A binary search tree in computer science, it is also called an ordered or sorted binary tree. This tree has a specific property, and that property is for any given node, let's say 20. The value of this node is greater than all of the keys in the node's left subtree. So this is the left subtree, left. This is the right of its subtree. The node's value itself is greater than all of the keys in the node's left, but less than those in its right subtree. So as you can see, 20 is less than 27. So if there is any keys after that, those keys have the same property that I just stated, that all of the values on the right in the subtree would have values greater than 20. All of the values on the left would have their values less than 20. So this is the binary search tree in the upshot. Let's just suppose that we have a sorted list, and this sorted list is implemented using either a linked list, array, or BST. If you recall, for a linked list implementations, what is the find efficiency in terms of the amount of time it requires to find something in a linked list? This linked list is sorted. In order to find that location, you basically have to go through this one at a time. There's no way you can jump right into it. This is how linked list is constructed. So that unfortunately gives you O of n in terms of find. But what about array, sorted array, O of log n, right? Because you can do what's called binary search. Binary search jump right in the middle, immediately branches is into either the left or right hemisphere. Depends on the target, whether the target is greater than the middle one or less than the middle one or equal to it. This is O of log n. Let's take a look at the insertion. So insertions in linked list basically says when you find that information inserted at that location, and that insertion is 3 operations times O of 1. For linked list, any insertion takes place just by swapping these pointers. So that's O of 1. If you have an array-based sorted list, insertion is O of n. And the reason is very simple because once you find it, finding is extremely fast. But insertion means that you have to insert that node and then to shift all of the elements out by 1. Insertion is pretty bad. Binary search actually combines the best of array and linked list. In general, the find operation or search is O of log n. We established that. Insertion is O of 1 because let's just say this value 9 is to insert. Finding that information is O of log n. Then you have to reposition these pointers to ensure that 9 is inserted right in the middle. These swapping of reference pointers is O of 1. You have to swap out the original one to point to here. This 9 will then point to 8. 2 times the O of 1. So in general, insertion is O of 1. In summary, why are we using BST and why is BST so good? Because if you just look at the best of insertion and find, binary search BST, basically the best of linked list and array. This is the reason why we're using a tree structure versus an array and linked list, because binary search tree gives us both search and insertion efficiency much better than linked list and an array will give you.